All right, welcome. We are in this lesson and the next lesson, we're going to be taking a look at database stuff, since ultimately that's a lot of what we're doing with our computers at any point is treating them as a database. So what I will do here, let me get the chat back open too. All right. So what we're going to do a little bit at the end of today, and then a lot more in 2 weeks, is we're going to build a little database called Archive, which will implement some SQL-like instructions, like a simple grammar, and it'll have a database backend store. And we're going to start off in this lesson by examining what is kind of the most fundamental primitive of data storage in Hoon that's more complicated than a list, which is the tree. Most of you have probably not looked at trees in much detail. You have used the things that are derived from them, namely sets and maps, which we do use pretty extensively. But tree itself is actually pretty primitive, simple type. It's a great type to build other things on top of. So let me just make sure I'm up to date there. Not that anything's going to have changed in here. Let's see, let's go to, all right. We're going to start here in Hoon.Hoon. We're going to be jumping around. So tree is a mold generator. And so what this means is it receives a type, in this case, the type of the node, and then it produces a mold that sort of logically describes a binary tree of values and then left and right subtrees, which can be single values or otherwise organized. It's every noun is a binary tree. So ultimately this is a binary tree, but the primary cell-based binary tree nature is not sort of the way that we're going to think about this tree. For one thing, a regular cell with a left hand and a right hand element doesn't have its own value, right? It's if we refer to let me do letters here instead of numbers just to be less ambiguous, right? So if we ask for what is the value at 1, then that's going to give us the entire data structure, right? There's no notion of value at a particular point. If we ask for value at 4, then we actually do get A and so forth. In contrast, tree is going to have it's going to have some root, and it's going to have a left tree, a node, and a right tree that are associated with that. And then the left and right tree can themselves just be single values or farther down into what is going on here. Now, I think this is intuitively, this is just kind of a simple model where we have we can actually have a value. We can have a value at each node, and then we're carrying everything else around next to it. When we look at how this is actually built, right? So we're going to define this with a buckpat, which switches on its sample as an atom. So if it's an atom, then it'll generate, in this case, null. Otherwise, it's going to generate a recursive subtree. So this is how this tree mold generator is going to enable it to produce empty nodes when there's no content in a node and we just have a sig value at that particular point. So there will always be a left tree and a right tree if there's a node. But the left tree and the right tree can both be sig. They can both be empty as well. So for instance, how do I want to do this? Maybe I'll split it horizontally this way. Now, let me just run the Zod that I have here. 2.3, okay, well, that's fine. All right, so if I give it this data structure, this is a tree. And so there is a node which has the value 1. There's a left subtree which has the node value of 2, and a null left and right subtree, and then a right subtree of the top that looks like that. So in our notation over here, it'll look like this. All right. So this is going to give us a lot of flexibility in defining branched storage structures. Trees are going to be preferred where hierarchical data are being represented, or data that we're storing with some sort of notion of order or structure that's more complex than like what you get with a list, right? Like a list only knows about order. And this is both a strength and a weakness, because it means if you need to do certain kinds of operations, you have to traverse the entire list. You're working with it in a certain way. We're going to use trees most notably in Hoon to define sets and maps. We're going to do a deep dive into maps in a minute. Those are both also mold generators that are built on top of the tree. So if we're going to work with a tree, we need to be able to do certain kinds of things with it. So we'll see what these look like. We'll build some of this, and we'll see some of this from the standard library. So we need to do something like enumerate items. So these are just sort of like standard things you might want to do if you have a tree. Search for items. Add or delete items. Related to that, prune or graft entire subtrees. And things like find common ancestor of 2 nodes. All right. So this is going to require us to have a notion of position inside of a tree. If I have a data structure that actually looks like this 1, 2, null, 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 I could number it according to the standard, noun-based binary tree layout and identify the values in that. This might get kind of sticky and complicated as I'm using that because of the way that running rightward cells and so forth are treated. So, maybe I settle on that, maybe I don't. Some of these are simple, right? If I want to prune out an entire subtree, in this model, I'm just replacing the left or right subtree with sig, and it's gone. All right, I've blown it away there. If I want to add it in, then I just recursively add it in at that point. So one thing I might want to do is do a depth first search in my tree. Given a tree of atoms, I'd like to locate the first time a value occurs inside of this tree. We can do this 2 ways. We can do a depth first search or a breadth first search. So a breadth first search would be, if we're looking for the value, let's say this tree goes deeper and we're looking for the value 3. In that case, my search order would be I would search 1, then I would search 2 and sig, and then I would search sig, and then I would search 3, and then I would return that I found the value. That would be a breadth first search. A depth first search is going to go down the left branch before it goes down any of the right branches. So it will search 1, then 2, then sig, then 3, and it'll return the value out to you at this point. There are some theoretical reasons why you might prefer one over the other, depending on how things are structured. Since these are basically, these are binary trees with a value at the node. So depth first search is going to tend to be more efficient for this because we're going to branch down before we branch across. You can have trees that are very broad n-ary trees, but that's not the situation we have here. So our basic algorithm in this case, so we'll call this DFS, right? Depth first search, would be we're going to check the current node for the value. We're going to, if it's not there, then we're going to look left first. If left is not null, we're going to descend left and we're going to start the algorithm over again. If it is null, then we're going to look right and start the algorithm over again. And if it's null on the right, or whatever, if they're both null, then we ascend back up, right? We pass out that we haven't found this yet. So it'll search each subtree recursively down into it and then pass itself back out. Now, the code that I came up with that illustrates this, actually, that's across here. Let me give you this code as well. So what search is going to do is it's going to, in this case, this search is going to translate the tree address to a numeric address. So given a value in a tree, we're going to return the numeric address corresponding to its position as a unit PAT-UD, where PAT-UD is the address, or since the unit null for absent. So this is for a tree PAT, a tree of atoms. We are searching for the needle in the haystack. Needle and HSTK are the syntax used in the list search function, for instance. We're going to start at a depth of 1. And the reason we need to keep track of the depth is we're going to use peg here in a moment. We'll come back to peg. We're going to run a trap. We're going to turn a unit PAT-UD out. We're going to sigpam the tree where we currently are. If our tree is null, then we're going to return null back out from this. So if we get all the way to the end and there's nothing left in our tree, then pop back out. If our needle is our current location, then we're going to return this sum peg depth 2. Otherwise, we're going to have a value L, which is the result of recursively searching into the left subtree, supplying this value peg depth 6. And if L is null, then we're going to search the right subtree. So if nothing comes out of this, then we'll just get a null out the end, value not found, we move on there. And so this will allow us to locate within a tree, what's going on with a particular value. Now, peg is interesting. This is our axis within axis. And so this is sort of, this is our relative, if we're in the urbit noun tree, so our regular 1, 2, 3, 4, 5, 6, 7 noun tree. If I give it the axis, I'm at location 3, but I'm at location 3 relative to location 7, then it will return to me 15, because that's the axis inside of the subtree inside of the overall tree. So peg is useful when you're trying to locate something down inside. So what we're going to adopt here for our convention is that we are simply going to return the axis address of the value that we locate inside of this particular tree. Now, if I've defined this correctly, let me call this all right, let me call this DFS1. All right, and then I have a example tree here. We'll just call data. And I guess call it a tree pat just for clarity there. All right, so there's a tree. You can see that the order kind of gets scrambled in the printing here, but you can sort of reconstruct it like 3 is the leftmost branch, 2 is the node above it, 4 is the right branch of that node, then the 1, then the 6 and the 5. All right, so we can sort of piece together how this looks. So now I should be able to do search DFS1 data for 6, and it should give me the overall. Yeah, so it gives me my search path, the tree at each point until I locate that value. And so now that I know that that value is located at access address 60 within the tree. So I should be able to do less 60 call data. Yep, and I've successfully located that value. So this is a depth first traversal. Sometimes it's going to be more efficient than others. If I were to search for 5, that's kind of my worst case scenario because it has to traverse everything to actually locate this. When you're writing these kinds of tree operations, you end up doing a lot of sort of recursive searches left and right to do that. Now there's another related problem that we can write out here. Let's call this flatten. And so this would be, can we convert a tree to a depth first search ordered list? Which means that as we go down the tree, for instance, in this tree, this would result in 1, 2, we throw away the null 3, and then if there were anything on the right-hand branch, we would pick that up as well. So this would actually result to 1, 2, 3 and a depth first. Well, in the definition of depth first that I'm using here, because you could also argue that you want to go all the way deep first before you add it to the list. But this one adds each node as it encounters it before it steps back left and right. It'll work for what we're showing off here. So what we want for flatten is we want the ability to ingest a tree. Don't know why I'm 4 over instead of 2 over. We want to return a list pat. And if our tree is empty, we can set our recursion point at the top. I don't think we need a trap here. If our tree is empty, then return the bunt of list pat. Otherwise, we want to search left and right. So this is always awkward because we have to basically set an there's probably a way to not set an intermediate variable, but this is the way I always do it. So I would define an L that is essentially we want to skip null values, right? We don't care about them. We're not adding null values to our entries here. So I'm going to run skip flatten on the left node, and then I'll have to define some sort of gate to test whether or not something's null. And it'll have to be a gate because I can't pass a rune in, what sig, I couldn't do that necessarily. So what skip does is it has a test, and if that test is true, then that value is not included in the operation. So we're going to define an L and an R, which are going to be the results of the subtrees here. And then I'm going to weld L and R together. This is the point that I would change if I were changing the order that I'm thinking about depth first search. I would put n.tree after this instead of before this, and I'd have to append it properly instead. All right, let's go to is null. Let's see, this should test. Let's accept an atom, and it will simply send.y, send.n based on whether or not that atom is correct. All right, if my logic is correct, then that should correspond to the prefab code I have somewhere else here. There we go. All right, looks like the cooking show worked. So tis DFS2. All right, so now I'm going to try flatten DFS2 on data that I had a moment ago. And that does give me 1, 2, 3, 4, 5, 6, which per the definition I chose for depth first, that's correct in this case because it's going down the tree. If you wanted to go up the tree, like I say, you'd have to mess around with this clause right here to change that behavior. As this is App Workshop, I'm going to leave you a couple of exercises. One of them is to get the breadth first search of the tree. What would it look like to modify the search algorithm to search breadth first? And you could have the same node multiple times in a tree. So you would encounter potentially a different address as your answer in a tree that doesn't force everything to be unique. And then there's a challenge as well to number the nodes in a binary tree in a way that you can give it a cell of data, and then it will produce a cell of the addresses of each value at the same location. So it'll be a simple binary tree, but it gets you sort of thinking through the same sort of logic, like what's going on with peg and so forth, as you recursively step down into things. Questions about tree? And if there are not, we're going to take a look at map. All right, we're going to jump to map, also in hoon.hoon. So this is a bar buck of a buck bar of a gate. It's kind of a funny little builder here. So it's going to build a mold core on the basis of a key value pair. That's your main input. Then it is going to produce a mold on the basis of, it's a tree whose entries are pairs of keys and values. And then it is going to apply this validation gate at the end. This is what buckbar does. Buckbar lets you apply a validator over whatever you have. And this is interesting to us because there's a lot of cases where we actually do want to validate the kinds of things that are inputs for a particular type. So at the Hoon School level, people would give us questions like, well, let's say I wanted to define a type, but it was only numbers in a certain range or something like that. And we say, well, you can't exactly do that. Well, you can, but it requires you to go deeper into buckbar and figure out, okay, like what would my validator look like for my true false to actually build that sort of thing. So in this case, the validator, the heavy lifting is being done here by this apt by. Apt is the correctness checker. We're going to come back to it later on, see exactly what it is doing, but essentially this is going to say we're building a map and we're making sure that the map, the tree of key value pairs is correct per whatever a map's requirement is. Going back to Hoon School, you'll remember seeing things like colors here. All right. So colors has a node, and then it has a left subtree, and it has a right subtree. And the order that we created the values in color are red, yellow, green, blue. And then we cast it to this map, pat TAS, pat UX. The order that they are in the map is in the actual map is that green is at the top. Beneath it is blue, whose left child is red. It has no right child. And then the right child of the overall thing is yellow. So the question is basically like, why, like, where is this coming from, right? Like we have the structural layout that looks like this. If it fits. Oh no, it doesn't quite fit. All right, that'll work for now. So we have the structural layout where it's branching left and it's branching right, but the order that these things are in there basically has no connection to the order in which we created them. So there's some internal logic on why this is the correct map and why other other trees that structurally contain the same information, they logically contain the same information, but their structure is different, would not be a valid map because they wouldn't pass whatever the test is that's being put forward by apt. Now, the reason that we care about this ultimately is that the order is how we are going to efficiently look things up inside of this. This is sort of like why we bother with a map instead of a list, for instance, or a set instead of a list, right? I mean, they do kind of different things, but a map lookup time should be substantially faster than a list lookup time. In average case time, a list lookup is going to be of the order of magnitude of n of the length of the list. But on average case time, a map lookup should be log of n, assuming a balanced map. So the question is, why are these entries ordered the way they are? Right? They're not alphabetical. They're not, there's something going on here, but it's not apparent from the outside. What map is actually using and what apt is doing in this case is it is ordering the real map on the basis of hash ordering, which means that it is building a tree where the mug, which is the hash of a value, the mug of red sorts before the mug of yellow, sorts before the mug of blue, sorts before the mug of green. Did I do that in the order that makes sense there? No, red, blue, green, yellow. Red, blue, green, yellow. Red, blue, green, yellow. And this is a little bit more apparent if I do this in hexadecimal, I think. Yeah, because they all come out to the same length in hexadecimal. So while we can structurally write trees that look like they would behave as if they were maps, an actual map as a type in Hoon is mug ordering the keys. There are several valid ways to order nouns according to Hoon orthodoxy. There is an AOR, which produces alphabetical ordering. These are probably in Hoon.Hoon. Yeah, so noun ordering. Yeah, there's a whole section here. So alphabetical ordering. There is depth ordering, which we're not interested in directly here. There is Gore ordering and more ordering. So one of them is sorting by the mug or the hash of a particular noun. And the other is sorting by the hash of the hash. That we're running the mug of mug, which randomizes things a little bit more. But right now, what we're interested in is Gore, right? It's mug order. So apt by is going to need to check whether the left subtree at each node is numerically less by mug order of the key than the node value, and then that the node value, or excuse me, the node key hash is numerically less by mug order than the right subtree. Then it'll check recursively within each of those. If all of these aren't true, then the tree is unbalanced and it's not a valid map, which means it won't give you the guarantees about lookup time and everything. This is this is in, so I actually want the next one, which is in by. Yeah, I'm in by. All right. So here's our actual logic for apt. It's a little bit complicated. So, all right, so the first line is checking that the left subtree is mug ordered relative to the key of the node at the current location. A in this case is given to the parent door as the sample, essentially. So A is a given here, it's the tree. Then we're going to check the order versus the right subtree. Then we're going to check recursively on the doubly ordered mug value. And I'm not actually sure why we have to do that as well, but we do it for both. That might be to get the node, like the node rather than the left or right value correct there. Anyway, this maps it all together here. Now, one example that we're going to use, this is from the documentation, and I think it's kind of an interesting one. So this uses malt instead of my. We're going to look at malt and my both in a moment. So this produces a map of keys A, B, C, D, E, and values 1, 2, 3, 4, 5. All right, so that is what A has. And I can ask it things like apt by A. I already know this is true because I built it using malts, and which would already have checked that for me, but you know, I can change it. So instead of that, let me modify the values inside of this. By manually changing the key in A to Z. So the key at the top, or from B to Z. So this was B was our root node. I'm going to manually change it to Z here. Same node, but I manually changed the mug. And now if I apt by Z, I get the answer no. And so we check this by actually looking at we can look at mug, I guess E, mug Z, and mug, what's to the right here? D. All right, and so mug of Z doesn't sort in correct order here. Mug of A, or sorry, mug of B does sort between mug E and mug D. So what this means is that even though Z is logically a tree, if I try to retrieve a value from it, if I ask for Z, I get the value back out. If I ask for A, I get the value out. If I ask for D, it fails because the mug order is wrong, which means in this case, it means it cannot search to the right because it's only looking at the order of the hash values to decide whether or not it needs to descend down a particular tree. In this case, it can't, so it sort of just ignores the existence of the D cell on the right-hand side there. So it's an interesting problem to have. Strictly speaking, you know, you could use trees, Hoon trees, to build all sorts of data lookup structures. And you can do this kind of analysis with set, for instance, or you could imagine building a map that is ordered differently. So you could change the map to be on alphabetical order. Why do you think we use the mug order, the hash order, rather than, like, say, alphabetical order for sorting these keys? No takers? As far as I can tell, the answer is that this is, in being essentially random, right, like unpredictable from the outside, this seems to be more likely to give you a balanced tree where, you know, there's a 50% chance at each branch that it goes to the left or the right of the current node. And so your tree self-balances to some extent, and you don't have to worry about efficiency of lookups, because there is no self-balancing aspect to this, right? Like, it's a map is dumb. A map is simpler than that. Now let's look inside of get, which is doing a lot of work for us as we use get, and anytime we use got or gut, then we're also using get to do that. So here's get. It's a bar tar that does a very interesting first statement there. Starting at the bottom probably makes the most sense for legibility here. Yeah, let's read it from our lower checks upwards. So based on the mug ordering of the value we're searching for against our current node's key, look left or look right. All that's saying there. If it is the current node, then return it as a unit. If we are empty, if we have reached the bottom of our search tree, we don't do a depth first search in this case. The get does not search every entry. Get only searches on mug order. So if we get to the bottom and we haven't found it, it's not here, right? That's the assumption that we're making. It's going to return out of the trap. It's kind of a wild little statement here. All right, so it's a unit of a cab, what gar, of a what tis, ket a, q.n.a. In English, it's a unit of the type of the value after assertion that it is a cell, which is a key value pair. Which kind of makes sense. Then the statement above it, this is also kind of a wild one. I like this one. This is saying recalculate the current subject by replacing B with the unit of the sought for value, including the type assertion. And then that's your result coming out of your what gar. All right, so the tick marks in this case here, this is the type assertion because you don't know the type of a map here, right? Get does not know anything about your map type. When I wrote flatten and search a moment ago, I punted on the question by just saying, well, I have a tree of atoms. If you don't actually know what your tree is, like we don't know here, we have to build a wet gate that can take a noun. And then once we have the value out, we have to reassert the value back on top before we return this value back out of our current case here. So it's kind of a fun, complicated statement where we're actually starting to think deeply about how do we handle type if we don't know type. We're not quite into vase mode, but we're getting right up to the line here as we look at this. Let's look at put. How do we put something inside of a map? All right, put is kind of long here. So what put is going to do, if we look at our what's here, we can basically infer that there are 4 cases. So we're receiving a key and a value. B is our key, C is our value. And it's a bar tar again, it's a wet get again, because we don't know in this gate what the type is yet. So we have to plug in the type live to do it. So B is our key, C is our value. And we're going to return something that is of the same type as A, which is our tree built with sample. So we're actually returning the tree built with the sample. And we're going to have to, if we correctly build put, then it should pass apt. But we actually don't actually run apt again anywhere inside of this. We just correctly build it. All right, the first case is that we are currently in an empty node. We came down to a null entry, nothing in our tree, whatever, at this point. in which case we insert a key value pair at n, and there's no left subtree and there's no right subtree. That's your simple case. Just insert the key value pair. Our second case says the value of our current key matches the head of our node. And in this case, this means that we need to match the key, we need to replace the key value pair. So it actually checks and says, is the value the same? If the value is the same, just return it. If the value is not the same, then recalculate A with the change of n made to a cell of B and C, and then return that. The third case is that the value of the current node is greater than or less than the current value. When I'm saying value here, I mean hash value. The hash value of the current node is greater than or less than the current value. We have to look both ways. So if we're at the bottom, we need to insert a current single node of the current node's value and the new value. So basically we assert that there's a cell, we plug this in, we reset the side of A with what is the current value, moving down the left or moving down the right, one way or the other, and build it that way. If we're at the bottom, then we just insert. If we are, let's see what we are. Yeah, if we're at the bottom, we just insert. If we're not at the bottom, then we need to dispatch the value recursively down in and continue to search into the left or right daughter subtree. So that's a lot, right? It's a little bit complicated there. This is why we're digging around in Hoon.Hoon. So I'm going to give you an example here. I'm going to give you, we're going to have a dictionary. We're going to insert, I'll call this Greek. All right. So Greek is going to insert alpha, beta, and gamma. Then it has to do it in hash order. So my leftmost hash is actually alpha. Beta and gamma are both to the right of alpha. And it turns out these are actually in order. Alpha, beta, and gamma, the hashes of these are sequentially alpha, beta, gamma. So our root is alpha, nothing to our left subtree. Our right subtree is beta at the root, nothing to its left, and then gamma to its right. So if I wish to add another key value pair, let me add delta here. Delta is going to sort to the right. All right, so if I search and put this to the right, then I can see that delta now is over here. It becomes the node, and then gamma. Yeah, the node is this value, and then gamma sorts to the left of it. All right, that's a little bit tricky. Let me show you that version there. And so this is why our order looks the way it does. We have alpha, then beta, then delta is the node child, but gamma sorts to the left of delta. So even though gamma was the third value entered, and it sorts to the right of beta, the way that this is accomplished is by putting it below delta, which is a little bit complicated. If I were to put, in this case, I'll go ahead and do epsilon. You can read this, you see alpha, beta, epsilon sorts as the center node, and then its right child is delta. Yeah, so alpha, left empty, right is beta. Beta, left empty, right is epsilon. Left empty, right is delta, left is gamma. So let me, I do have a diagram here, but it is actually incorrect. So I'm going to hot fix it and then share it with you. All right, so now this is this bottom one. So alpha, beta, epsilon, delta, gamma. So this is a little bit of an interesting example because this tree is actually unbalancing by itself. It's not so deep yet that it matters, so we can kind of trust in the law of large numbers to save us should we continue to add things to this map. But this is what the traversal would look like as we built this. All right, back to Hoon.Hoon. We're going to look at my, which is our map constructor. You will recall, let's see, I think I used an example of my earlier, didn't I? With colors, maybe. Yes, so my accepts a list of pairs and produces a map. It will infer the type wrong because it will infer it as a union of red, yellow, green, blue, but that's just because that's term peculiarity there. So the way it's going to build things, we need to see the list constructor because LE is up here. But what we're going to do is it's going to actually just run gas by over this empty one and then insert an A into it. So map cab p.I .hep.a map cab q.i.hep.a. Right? Like this is kind of a complicated one because it's just figuring out like what is my actual value here. Now, because I am doing this inside of a WetGar, two expressions composed together, I then, for each entry, it's going to recalculate A in the current subject and then run gas by again on the next value that is coming through this. And it's going to keep doing this until this actually results in a final value, which is why we have this list constructor up here. Probably the most interesting thing about this list constructor is this. Has anyone run into BARPAT before? This is a wet core. So we have wet gates, now we have wet cores. And we have to have a wet core under certain circumstances to, well, we have to have a wet core to build wet arms. But in this case, it doesn't even have wet gate as a child. It just has a buck that is getting immediately invoked. So what it's doing then is basically just saying, you know, can I construct a list out of the values that I've been given in this particular case? And so that's what's going to keep running as it does this. You could think of this as running homogenize on the list value first to unify across all the types and make sure that it behaves correctly here. Gas is not super interesting because it's a recursive put call. So what we saw in put already happens as well. So there's some funky logic to satisfy the type checker the same way that we're running into here, but otherwise gas by is not particularly interesting. There's also the old map builder. Oops, wrong one here. So we have malt and molt. And then let's see, I think I did have a copy pasta of mine. So we can compare, in this case, we're interested in comparing malt to my. So malt is the old one. It works the same way as my, but it's the old map builder. It's available, but it's kind of been informally deprecated. So among the reasons you might not prefer malt is that it doesn't explicitly cast to map. and it doesn't homogenize its list first the same way, because it's just kind of dumping it through this list pair builder here. Some of the internal logic ends up looking pretty similar across both of these, but you'll notice that it is a tree, cast to a tree, not cast to a map. So minor stuff. When I was asking about some of the logic behind like why we prefer my over malt, Joe Bryan said he actually thinks you should just use GasBy directly, recursively, rather than trying to use my or malt. But it does stand that my is pretty simple and straightforward to use. All right. Let's see, that's probably enough of that. One of your possible exercises for this is to do a similar sort of deep dive through set and in. They're a little bit easier logic because sets are simpler than maps in many ways, but they're also trees, so you can dig around in them. All right, so let's talk about databases, right? All right. So how does a database differ from a map, right? Like what's the idea of a database, right? The idea of a database is that we have some sort of structured data and some way to look up values inside of this structured data table functionally. Hoon's map is close to the simplest possible thing that you would actually want to call a database. And for instance, TomeDB, I looked at it last few weeks ago, and I don't think it's substantially changed its internal architecture, but it's essentially a wrapper over a map of key to value, right? So the simplest database is a key value store. So it's a map, it's a hash table, it's something like that. Hoon's hash table is a map. So in a sense, a map already is the database. What is frequently different in databases is that they tend to implement logic over the top for queries and management. You can do things like rebalance the data structures so that they're stored more efficiently. Basically you have a database management system that's doing more than what just like a bare hash table or map is doing. And over the years, there have been a lot of different ways of thinking about hierarchical or relational or object relational databases. One of the more popular ones in recent years is the document-oriented database. This is like NoSQL. So sort of broadly speaking, when people talk about contemporary databases, they're either talking about SQL databases, which are relational databases, and it has a lot of tables or views internally with one object might be represented in multiple tables or multiple views, and you would encounter it in different ways depending on the kind of query that you had over the top. And then a document-oriented database is set up so that it can efficiently search over metadata or over values inside of a document. The architecture that you choose for a particular application is determined by a balance of your representation, your query logic, your speed needs, all of these kinds of things. Classically, when we talk about a database, we're talking about CRUD. All right, so CRUD is the old acronym for create, read, or retrieve, update, and delete or destroy a record. In practice, creating records tends to be pretty straightforward. Updating records tends to be also, if you can create a record, you can update a record. If you delete a record, you can update a record. So read tends to be the most complicated part of what's going on. If we want to implement a database in Urbit, like I say, next time we will look at several existing examples and we will try to construct our own called archive, our own simple one. We're going to need a few components, right? So we need an interface, right? So we could call this, this could be a REPL or it could be a code, but basically this is text to action. Right? We have some way of coming from what is my user's intent to what is the action that I need to perform. Then there needs to be a command processor. Doesn't mean we're going to be writing a shoe sole app, but yes, we are, because ultimately we have to type these things in. We could do it all through generators, for instance. It wouldn't be that big of a deal. Our command processor is basically action to event, right? Like what does this translate to in terms of the internal logic of the system? And then there's the actual database backend, which goes from event to data, and then the data come back out to us in whatever our form. In practice, the interface could be an HTTP API or a JSON API. Could all be built through POX and Urbit. Could be command line or generator driven. We could do this a lot of different ways. At this lesson, I want to conclude by producing the database superstructure along with some of the input-output logic that you run into in doing this. There's a caveat here that there's a couple spots where my logic is not quite working the way that I want in my expressions here, but we'll get that fixed next time. So we're going to call this archive, RKYV, because I decided that something that I always forget how to spell is a brilliant name for a desk. And the data structures that we need to make this work, we're going to have a key value pair. We're going to build this as a document-oriented database. So it's going to be able to store an XML document. This is actually old code. I don't need that there because I'm already in spec mode. XML, JSON, YAML, or text documents. What we do with those, that's kind of a different question, but this is the way we're actually going to build them. We're going to have head tagged for each of these so we can distinguish them. Our actual data store is going to be a map from key to value. No surprises there. We're going to have a cursor abstraction. Cursors are frequently used in databases because you need to have the ability to keep track of locations inside of the database. You could pull the value immediately, but like, for instance, if you were searching for the minimum value in a database, you would use the cursor as a way of not having to pull the data every time you find something that's lower. You decide that, well, given the structure of this database, maybe it's easier for me to do a lookup every time I need to do a comparison beyond like what's in local memory. So a cursor abstraction, we're going to use that PatUD. We're going to use it similar to our depth first search. It's just going to be an index into the axis of our map. Then we're going to have actions and results. Actions are going to be create, retrieve, update, destroy. No big surprises there. The retrieval logic, we're going to be able to build more complicated sorts of compound retrievals on top of this, but right now this is a key lookup. That's all that's going on here. And our results are we can restore the entire, we can return the entire data store. We can return the value that corresponds to a key. Or this one might be dubious, but right now I have it in there where we can return the key when it is deleted for someone who's keeping their own local copy of the store. That may or may not turn out to be the best idea, but we'll worry about that later. Our marks for action and results have nothing special. There's a noun arm in each case. Ultimately, the result arm should probably have a JSON arm. I'll defer that for right now. Maybe I'll get a chance to build that before 2 weeks when we come back and try to actually implement this. And then our app logic is kind of where interesting things are happening. So this is app archive.hen. All right, let's import our structure file. There's our version state. The only thing in our state is our data store. No helper core, nothing with onload. All right, our poke logic is most of what's interesting. We are going to assert that all of our pokes are local, or they are from locally authenticated sessions. Ultimately, we are going to assert that we are only receiving archive actions. We're not going to handle nouns and try and coerce. We're just going to receive archive actions. Later on, we may want to go back and have HTTP responses as well. And we're going to switch over the values that we're getting from this. If the head is create, then we are going to put the value in our data store of key and action. We're going to give the fact of the resulting store back to all subscribers. Then we're going to kick all subscribers. This is there are several ways of thinking about returning data to people in a pub sub architecture the way that we have. I have normally preferred to just give the gift back and leave it at that. After talking to Hodzod and some others about what they are internally doing in their code, I've decided to start experimenting with giving the fact and a kick at the same time and requiring them to resubscribe every time they send a value. We'll see, what we actually prefer in the long run for this pattern, but this is basically what we have right now. To retrieve a value, this means that we're actually doing our lookup. So we're doing get by store. We should now be changing store. I was obviously copy pasting here because the actual logic for this should look a little bit different. We don't have a value act. We have the value retrieved. And then we do not need to make any changes to this. All right, that should be correct. All right, we're still head tagging with value because that's our archive result. Our update requires us to change the data store. It returns the value. Arguably update, maybe there should be an ACK or something. I haven't quite decided what to do with this. So I might turn this into an ACK by the time we start building out the final logic in 2 weeks. And then there's a destroy, which in this case deletes the value in our store, and right now returns a notification back that a key was deleted for anyone keeping a local copy. And then our peaks in this case are we can look at the entire store, or we can look at a key by what that key's value is. And I'm using gut by, which gives you what the default, and I'm returning send null in the case because I didn't want to deal with units at this point. That also may be a questionable decision, and I may revisit that later on. On watch, basically returns when you subscribe to store for the first time, it returns the current store. When you subscribe to a key for the first time, it returns this. That is an artifact from when I was typing in Vim a moment ago. Oh, that's why. Okay, there you go. Close bracket. There we go. All right. And ultimately, this sort of gives you the idea of if we're thinking about building an Urbit database, here's the things we have to be able to do out of the gate. We actually want to handle these operations explicitly because as an agent, we just need some sort of way of wrapping the map logic behind it. Now we're only using a map, right? We aren't doing anything fancy with this, any deeper kind of analysis. We could, right? Whatever store is in a future version of this, we could change this. We could decide, well, we're not going to use a store. We're going to use a custom implementation that balances alphabetically, or is just a tree of pairs of keys and values, and we are manually traversing it. We're not using the BY core at all to interact with it. So these are all decisions that we could make and change at some time in the future if we decided we did not want to use Urbit native maps to make this happen. Now, when we start building the grammar for this next time, right? Like what do commands look like in this? We are going to have to think very carefully about, like how do we actually, at that point, an efficient search may have different requirements for us than map provides. So for instance, we would potentially be saying, well, we would like to have it efficiently look up the, let's say the shortest values first. Well, obviously the mug of the key has nothing to do with how long the values are. And so we would actually then want to go back and say, well, whatever our underlying data structure is, tree or otherwise, we want to sort it differently than we are currently sorting it. And so this is when the actual logic of your language, your semantics, or excuse me, your syntax starts to impinge on how you are structuring your database, even aside from what you would be running into with respect to disk lookup times and so forth. Which right now, that's probably not our bottleneck for building a pure database on Hoon at this point. All right. Questions, comments? What do we have for today? That's my field of starting to think about database structures as we move into this. And in some ways, one of the more interesting ones that we're looking at, which is cursor, is actually super simple because it really is just an axis. Where are we in this tree? But we will use it next time when we start doing compound lookups.
Neil, is the fact kick pattern, is that specific to databases, or is that a good pattern for Gall agents broadly?
So I've been seeing it in applications where single values are being requested. You have a front end or something, it's requesting a single value. So it subscribes, and then as soon as it gets a value, it expects to be kicked. And then if it needs the value again in the future, it will subscribe again. It's just because we're kind of working around the fact that pokes don't have a reply. So if we need a value back, we have to get the value back as a gift. And so one way to handle that is to get the gift and send the kick at the same time. Is this going to end up being like universally the best way to do it? I don't know. Like I say, I'm starting to experiment with it here. But I doubt that archive is ever going to be used intensively enough that whether or not that pattern is the most efficient way is going to start making the determination. Maybe someday we will have front-end applications or something that are doing enough calls to the back end that we actually do have to do some studies on, is this the right design pattern, or do we need to just be leaving the subscription active, or is there something else we need to be doing?
Got it.
All right. If nothing else, I'll go ahead and wrap us up.